Now we will take some of the additional problems for our clear understanding of basic thermodynamics. So I'm just taking a problem for understanding the steady energy flow equation. So this problem is based on steady flow energy equation. So I'm just writing the problem here. Steam enters a turbine. Steam enters a turbine at 3000 kilopascal and 550 degrees centigrade and leaves as shown in figure. Calculate calculate the turbine calculate the turbine power output for an inlet velocity of 200 meter per second. Use enthalpy at one section is 3569.1 kilojoule per kg, and for second section, that is S2 equals to 2665.7 kilojoule per kg. Take specific volume at section 1 is 0.08643 meter cube per kg. Neglect kinetic energy and potential energy. So now I am just drawing the diagram here. This one is the turbine we are having. This one is the shaft work. This one is the outlet in section 2. Inlet. We are having the velocity 200 meter per second. Here dia is given 50 mm. Similarly here dia is given 250 mm. Velocity V2. Pressure is given 80 kilopascal. And X2, that is quality of steam. We will talk this term in the next chapter. That is 1. So now we have to apply, because we know that is a turbine is nothing but a steady flow energy system. So we can apply the steady flow energy equation, and in this equation we have to neglect the kinetic energy and potential energy. So after neglecting the kinetic energy and potential energy, we can write steady flow energy equation in this manner, that is Q plus H1 plus to W plus H2, because here I am neglecting the kinetic and potential energy of the system. And here in turbine there will be a no heat transfer between the system and surrounding, so I can write Q equals to 0. So now I am having H1 equals to W plus H2. So W equals to H1 minus H2. We are having the value of H1, that is 3569.1, minus H2 is 2665.7. So now W will be, now if we calculate the value of W, then it will come around 90. Calculate the value of W, it will come around 904. So we can write here W equals to 903.4 kilojoule per kg. So that is the value of W. But here we are interested in power. So we are having the work done in terms of kilojoule per kg. So now just calculate the volume flow rate first. So volume flow rate is nothing but A1 V1. A1 is the area of cross section at one point here. It is mentioned here 1, because the D1 is 50 mm, so we can calculate the A1, that is pi by 4 D1 square. and velocity is given, that is 200 meter per second. So now we can easily calculate, that is pi by 4. T1, that is 50 mm, so in terms of meter, that is 50 into 10 to the power minus 3 square, and velocity we are having 200 meter per second. So now this m dot will be 0.393 meter cube per second. So here I am saying m dot is volume flow rate. So the volume flow rate, that is m dot, is 0.393 meter cube per second. At section 1, that is V1 equals to 0.08643, that is meter cube per kg. So we can find out mass flow rate. Mass flow rate is nothing but m dot, that is volume flow rate, divided by specific volume. So 0.393 divided by 0.08643. So the mass flow rate will come around 4.55 kilogram per second. So now we are interested in power. So easily we can find out power. So power is nothing but work done into mass flow rate. Mass flow rate. So we are having the work done, that is 903.4 kilojoule per kg, and we are having the mass flow rate, that is 4.55 kilogram per second. So we are having 4110.5 kilojoule per second. It is nothing but 4110.5 kilowatt, and in terms of megawatt we can write 411.1105 megawatt. So correct answer is 4.1105 megawatt. Let's take one more interesting problem. I am just writing the problem here. Problem. So gas expands from pressure P1 P1 to pressure P2. Pressure P2. Here we are having P2 equals to P1 by 10. For isothermal process, if the process of the end of expansion, the process of the end of expansion is 0.55 meter cube. If the process of expansion is adiabatic, then find volume at the end of expansion. So here in this problem, first we have to go with isothermal process, and in the next part we have to go with adiabatic process. So let's go with isothermal process. So for isothermal process, we are having governing equation P equals to constant. So I can write P1 V1 equals to V2. Here in this problem, V2 is given, that is 0.55 meter cube. We have to find out V1. So P1 V1 we have to find out. P2 we know, that is nothing but P1 by 10. V2 is 0.55. So V1 here is 0.055 meter cube. So by first part we can find out the value of V1, that is 0.055. Now for adiabatic process, we are having the governing equation, that is PV to the power gamma is to constant. So we are having P1 V1 to the power gamma, P2 V2 to the power gamma. So here gamma is 1.4, that is for here. So I can write P1 V1 we already calculated 0.055, gamma 1.4. P2 is nothing but P1 by 10 and V2 to the power 1.4. So now if we solve it, we are having 0.1724 to the power 1 upon 1.4 V2. So V2 will be 0.25 meter. So the correct answer means volume at the end of the expansion will be 0.2. Let's take another problem. First writing the problem here. The air in the cylinder of an air compressor air compressor is compressed from 150 kilopascal to 15 megapascal. Estimate the final temperature and work required if the air is initially at 50 degrees centigrade. Consider the compression takes 0.01 second. So here in this problem we have to find out the final temperature and the work required. Here in the problem it is mentioned the compression takes 0.01 second, means the compression takes place very quickly. So if some process is going very fast, very quickly, then there is no chance of heat transfer between system and surrounding. So we can assume such kind of system as a adiabatic, such kind of process as a adiabatic process, and we can use adiabatic process governing equation for solving such kind of problem. So now we will start with adiabatic process. So for adiabatic process, we are having the governing equation PV to the power gamma equals to constant, and we know the perfect gas equation, that is PV equal to RT. From here V is nothing but directly proportional to T by P. So here we can easily plug T by P in place of V. So now I can write P1 1 minus gamma T to the power gamma, P2 1 minus gamma T to the power gamma. So we know in the problem it is mentioned P1 is 150 kilopascal. So P1 is 0.15 megapascal. P2 is mentioned 15 megapascal. Here T1 is 50 degrees centigrade. So in terms of Kelvin, 50 plus 273, it will be 323 Kelvin. If I put these values here, I will get 0.15, 1 minus gamma, that is 1.4, T1 323, 1.4, P2 15, 1 minus 1.4, T2 to the power 1.4. So now if I calculate like that, 0.15 power minus 0.4 into 323 to the power 1.4, 15 to the power minus 0.4 equals to T to the power 1.4. So now I can easily get 20554.8 to the power 1 by 1.4 is T2. And if we calculate it, T2 will be 1201. So the correct answer T2, that is final temperature 1201. Now on application of first law of thermodynamics. So first law of thermodynamics. So according to first law of thermodynamics, del Q plus del U plus del W. And for adiabatic case, for adiabatic no heat exchange between system and surrounding. So del Q equals to 0. So I am using 0 del U plus del W. And del U I know it's nothing but CV delta T. CV for air we are having 0.718. Delta T, that is 2 T1. So del U equals to 0.718. T2 is nothing but 1201. T1 is 323. So it will be 630 kilojoule per kg. So del U is 630. The value of del U in this equation, del U plus del W. So del W will be minus del U minus 630 kilojoule. So it is work done on system because it is coming negative. So work done on system will be 630 kilojoule. This one is the correct answer. Starting the new problem, let's consider some of the fundamentals of thermodynamics which are very important. So I'm just considering the perfect gas. So here in perfect gas there is a no force of attraction or repulsion between molecules. So for perfect gas there will be no force of attraction and repulsion between the molecules. And the second assumption in case of perfect gas, the mass of molecules is a point mass. Mass of molecules the molecules point mass. Point mass. So for perfect gas, we have to assume two assumptions. There will be no force of attraction and repulsion. For the perfect gas, there will be no force of attraction and repulsion between the molecules, and mass of the molecules is point mass. And the equation for perfect gas, PV equals to N RT. Here N is number of moles and Ru is universal gas constant. And its value of Ru is 8.314 kilojoule per kilomole. So this one is the equation for perfect gas, that is PV equal to NRUT. Similarly, we have another number that is called Avogadro's constant Na. I can write Avogadro's Cartwright's constant, and this constant value is 6.022 into 10 to the power 26 kilo per mole, and one more constant, that is Boltzmann constant. Boltzmann constant, and value for this Boltzmann constant is 1.380 into 10 to the power minus 23 joule per Kelvin. And now I can write Ru equals to NaKB. So there is a relationship between universal gas constant, the Avogadro's number, and Boltzmann constant. There is one more equation, PV equals to mRT. Here m is mass of the gas, R is characteristic gas constant, and now there is a relationship between R and Ru. R equals to Ru by m. M is molecular mass. Yeah. So now if we are having molecular mass, so we can calculate the characteristics gas constant R. Now I will define the standard atmospheric condition and normal atmospheric condition. First I will define standard atmospheric condition. So standard atmospheric condition, pressure will be 1.013 into 10 to the power 5 Pascal, and temperature will be 288.15 Kelvin. Similarly, for normal atmospheric pressure, atmospheric condition, pressure will be 1.013 to 10 to the power 5 Pascal, and temperature will be 273.15 Kelvin. So these are some of the important points we should remember, and it is very useful in solving the problems of thermodynamics. So now come to the point for perfect gas, specific heat. For perfect gas, specific heat is constant. Now for ideal gas, specific heat is a function of temperature. So now I will differentiate between perfect gas and ideal gas. In case of ideal gas, specific heat is a function of temperature, but in case of perfect gas, specific heat will be a constant. But both perfect gas and ideal gas will follow the perfect gas law, that is PV equals to nRT or PV equals to mRT. So in reality, we are having the real gases. So real gas having a force of attraction or repulsion, and they are not following the perfect gas law. They are following some other law that is called van der Waals law, that is P plus A by V square, P minus P equals to R. That is just for our understanding. In case of real gas, there is a force of attraction or repulsion between the molecules, and the real gas will not follow M equals to RT. For real gas, PV equals to RT. So real gas, PV is not equal to RT. So there are some situations where we can treat real gas as a perfect gas at a very low pressure and temperature. And very far away from critical point and very far from critical point. We can treat we can treat real gas as perfect gas, and we can use the equation PV equals to RT.